I am Anil Kumar. Welcome to my series on calculus. We'll learn in details how to sketch curves of rational function in this particular video. So the question here is, use the algorithm for sketching the function y equals to x squared divided by x minus 3. So algorithm means that you have to find all the important key parameters. Clearly mentioned here are: show full organized solution to determine the following: intercepts, oblique asymptote, vertical asymptote, minimum and maximum points, maximum, make a table for intervals for increase and decrease, point of inflection, intervals of concavity, and then we'll sketch the graph. So I like to categorize these activities into three groups. The first group will be to understand the characteristics of the parent function. And in the second group, we'll analyze first derivative, which is f dash x. And in the third group, we'll analyze the second derivative. The second derivative. Correct? In the very first category, when we are trying to find the characteristics of the function, we'll actually find out the three parameters mentioned here. So that will be our first category. Minimum and maximum points, increasing, decreasing behavior, this will be analyzed in the second derivative when we analyze the first derivative. And then the second derivative will give us complete information for the concavity and point of inflection. Once we have that, finally, we'll sketch graph. Is that clear to you? So let's begin with the characteristics of the function given to us. The function given to us is y equals to x squared over x minus 3. Now this is a rational function. So whenever you have a rational function, you should look for a couple of key parameters. Of course, intercepts is common for all, but the other parameters are horizontal asymptotes and vertical asymptotes, right? Sometimes you may have oblique asymptotes. Now in this particular case, we see that the degree of numerator is higher. So we have oblique asymptote. Let me write down the condition: degree of numerator higher. So we have oblique asymptote, not the horizontal asymptote. Okay, so with that in mind, let's find out all the parameters. Intercepts. To find the intercept, what should you do? So let us say we want to find x-intercept. So x-intercept means y equals to 0. So substitute y equals to 0, solve for x. This is only true when x equals to 0. And therefore, 0, 0 is our x-intercept. Well, clearly, that is also the y-intercept, since when y value is 0, the x value is 0. So the graph crosses the origin, right? So that means the point origin is on the graph. So let me highlight this point, which is on the graph. Now let's look into the asymptotes. To find the vertical asymptote, what should you do? Denominator 0, right? So which is x minus 3 equals to 0, and that gives you x equals to 3, and this becomes your vertical asymptote. So let's write down vertical asymptote is x equals to 3. So let's highlight this important parameter. Now, oblique asymptote. How are you going to find the oblique asymptote? Well, to get the oblique asymptote, you have to divide the numerator by the denominator. So in the numerator, we have x squared. We are going to divide this by x minus 3. Well, let me apply the placeholders here to do the needful. So we can actually now, it'll go x times. So you get x squared minus 3x, and when you take away, you get 3x, bring down 0, and now you can do plus 3, so you get 3x minus 9. So that is 9 for you. Now that clearly indicates that we have an oblique asymptote whose equation is x plus 3. So let me write down oblique asymptote will be y equals to x plus 3. So these are the parameters which we have found. So let's write down all this in our list. So intercepts, both are at the origin, so 0, 0. Vertical asymptote is at x equals to 3. And the oblique asymptote is y equals to x plus 3. Perfect. So that is how we are going to find the basic characteristics. Let's move and analyze the first derivative now. The function given to us is y equals to x squared over x minus 3. The derivative of this function will be, you can apply the quotient rule, we get x minus 3 whole square. Numerator derivative will be 2x times x minus 3 minus x squared times the derivative, which is just x squared. Let's simplify this. So we get 2x squared minus 6x minus x squared over x minus 3 whole square. And that gives you 6x squared, 2 minus 1 is x squared minus 6x over x minus 3 whole square. So let's continue. Do it on the right side. The first derivative for us is equal to, we can factor x and we get x minus 6. Denominator is x minus 3 whole square. Now that gives us critical numbers, right? So we have critical numbers, two of them. So whenever y dash equals to 0 or does not exist, we get critical numbers. So in this particular case, the critical numbers are at x equals to 0, x equals to 6, and x equals to 3, where it does not exist. So basically, we'll analyze these points. So let's analyze these points. We'll take these 3 points, we'll divide our plane into 4 intervals. So we have 1, 2, 3, 4 intervals. We'll write down these points in a sequence. So let us say all these values here are positive 0, 6, 0, 3, and 6. So these are the x values. So these are the intervals where we'll take the test points. Test points could be minus 1, 1, 4, and 7. The factors which we are looking at are x, x minus 6, and x minus 3 whole square. The values for these factors, for square, it is going to be always positive. So all 4 positive. For x, it is going to be same as the test point. X minus 6, this is negative, 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 and positive. And therefore, the end result of all the 3 is going to be 2 negatives means a positive, 1 positive one negative is one negative, and this is all positive. So we have positive during minus infinity to 0 and negative thereafter. Now positive and negative first derivative, which is what we are analyzing. Positive means increasing interval, negative means decreasing, then again decreasing, and then increasing. So clearly, we have our local maxima and minima. So at this point, which changes from increasing to decreasing, right? We have a local maximum. So that is your maximum point. And here we have a minimum point. So we have got 2 points, maximum and minimum points. So the maximum occurs at x equals to 0. So at x equals to 0, we have a maximum. So let's write down what we just got. So we have a maximum since the derivative changes from increasing to decreasing at x equals to 0. So when you substitute x equals to 0, you get y also equals to 0. And then we have a minimum at x equals to 6. So let us substitute 6 and find y. So 6 squared over 6 minus 3. So we have 36 over 3, which is 12. So that gives you a point which is 612. So we can write down that we have minimum value at, we can say local minimum is at 612, and we have local maxima at the origin. Interval for increase and decrease. As you can see, it is increasing in the two intervals. Let's write down here. So it is increasing in the interval from minus infinity to 0 and in the interval 6 to infinity. And it is decreasing in the interval between 0 to 3 and then 3 to 6. Now it's important to understand that x is not equal to 3. That is your vertical asymptote. So you should not include 3 in any of your answers where you're writing the intervals. Is that clear to you? So we have now found a couple of important things here, which I've listed above and calculated here. So we have a minimum value, we have a maximum value, which is at x0 and y0, and we have also found increasing and decreasing intervals. Let me highlight here itself. Does make sense to you? Correct? And we also know what our first derivative is, which is given right here. So we're going to use the first derivative from here to find the second derivative. So it is x squared minus 6x divided by x minus 3 whole square. So let's go to a fresh page. So we have found that y equals to x squared over x minus 3. We just derived first derivative as, let me copy, x squared minus 6x divided by x minus 3 whole square. Now, let's find what is the second derivative. So second derivative, we are going to use the quotient rule. So it becomes x minus 3 whole square of square will be 4 power, right? Derivative of the numerator is 2x minus 6 times we have x minus 3 whole square minus derivative of this, which is 2 times x minus 3 times x squared minus 6x, correct? Let us expand and simplify. We can take something common, which is x minus 3. So let's take x minus 3 common, and then we are left with 2x minus 6 times x minus 3 minus, on this side we have 2 times x square minus 6x. And then we have a denominator which is x minus 3 to the power of 4. So we can cancel these two to get this power as 3 and expand the numerator further. So when you expand the numerator further, we get x times 2x is 2x squared, then 2x times minus 6x, and then minus 6x, and you get plus 18 minus 2x squared plus 12x over x minus 3 cube. And that gives you, so you have a function which is, in this particular case, minus 12x and 12x, 2x squared and 2x squared. Well, this cancels. Okay, it simplifies. So we have 2x squared and minus 2x squared, they cancel. Minus 6x and minus 6x is same as 12x, that also cancels. So we are only left with the number 18 on the top. So that's good for us. So the second derivative now simplifies to 18 over x minus 3 whole cube. So from here we have one critical number, and so we can write from here that the critical number is at x equals to 3. So to find the concavity, we have a restriction here. Remember that. The restriction is that x is never equal to 3. We have a vertical asymptote. However, we can analyze either side of x equals to 3 for concavity, right? So we'll analyze the two intervals which are divided by this critical number. So let us analyze on the left hand side. So let us say that this is our reference where we are writing x equals to 3. We'll now analyze the second derivative, which is y double dash, taking test points as 2 and 4 on either side. Now on the left side, if I substitute minus 2 in x minus 3, it becomes a negative number. Cube of a negative is negative, and so what we get here is negative. On the other side, we get positive. So clearly the concavity is concave down on the left side and concave up on the right side. Perfect. Since the second derivative is negative, we have no point of intersection. Remember this, concavity is changing, but point of intersection, point of inflection does not exist, since that is a restriction here. Okay, so let's write down point of inflection does not exist. As far as the interval for concavity is, we have concave down in the interval minus infinity to 3, and we have concave up in the interval from 3 to infinity. Perfect. So we have found each and everything required to sketch a graph. Let us now look into the details of sketching the graph itself. So now we are going to summarize all what we have learned, and then we'll sketch the graph. So let's begin by mentioning the characteristics, which is x and y intercepts. So as far as intercepts were concerned, we got 0, 0, so it passes through the origin. Then there is a vertical asymptote, which is at x equals to 3, right? When the denominator is 0, x equals to 3, and we had oblique asymptote, which was, let's look into the characteristics, y equals to x plus 3, correct? So let's write down this value, y equals to x plus 3. These characteristics can be drawn on the graph. So let's begin with this. X plus 3 is an oblique asymptote. So it goes like this, like y equals to x plus 3, where this point here is 3 and the slope is 1. Then we have the vertical asymptote, which is 3. So let's draw this vertical asymptote, x equals to 3. Oblique and vertical asymptotes have been drawn, and we know that the curve goes through the origin. So let's continue with other findings. We got local minimum and we have local maximum. Local minimum was at 612, local maximum was at 0, 0. And we also found concavity, concave up and concave down. As far as concave up is concerned, it was from 3 to infinity, and concave down was from minus infinity to 3. At 3 we have a vertical asymptote, right? This is what we learn using the second derivative as mentioned here. Clear? There is no point of inflection, important to note. So we are saying this is maximum and that is a vertical asymptote. So how can you sketch the graph? Well, clearly we have concave down in this interval, so a graph like this could make sense, correct? So we could actually now sketch our graph from here, and the graph will look like it is approaching this oblique asymptote, turning from here and approaching the vertical asymptote. On this side, we have a local minimum, which is 612. So let me say that this point here is 612. So I'm calling this point here as 612, which is local minimum. So let me extend this. And so the graph on this side will be like this, where this point here is 612. Is that clear to you? Now, one more important thing to understand is why is the graph above the asymptote here and below the asymptote? So the question for you is, why above in this case and second is why below in this case? Can you answer me this question? All right, so these are two questions for you to answer. Well, the answer lies when we are trying to analyze the characteristics. If you see, what did you get? Now, in this particular case, you got a remainder of 9. So if you write the division statement, you will see that there is a remainder of 9 when you divided the function. So when x is large, when x is approaching infinity, in that case, we have a positive 9, right? We have a positive 9. That means above. But when x is approaching negative infinity, this will be below, right? That is kind of very important to understand. So let us see how we interpret this. So let's get back to our function where we have drawn the graph. We are saying we have x squared over x minus 3. We got oblique asymptote, which is x plus 3, plus we had a remainder 9 divided by x minus 3, correct? That was the status. Now if x is approaching negative infinity, in that case the function, let's call this as y is approaching this value is negative, right? From below. If x is approaching positive infinity, then y is approaching from above since we are adding something to it. Is that clear to you? So this is a very important concept which you need to take care of when you are sketching this part. So I hope that makes sense. With that, we come to an end of this particular video. We have understood how exactly to sketch a rational function. Now, in this case, there was oblique asymptote. I'll encourage you to look into more videos on this topic so that you get familiar with all other types. Thanks for your time and all the best.